Welcome back to Chemical Kinetics. Today we are going to look at the rate law. So the rate law is basically an expression that relates concentrations to the rate of the reaction. This is true actually only about the differential rate law. We will also look at what is called the integrated rate law, but in general when people talk about the rate law, they're just talking about the differential rate law. So it is only telling you how concentration of a particular reactant can change the rate of the reaction. So if you double the concentration, what does that do to the rate of the reaction? If you triple the concentration of a particular reactant, what does that do to the rate of the reaction? If you look at a general reaction where A and B are combining to form products, then the rate can be written as the rate is proportional to the concentration of A raised to some number m and the concentration of B raised to some number n. The thing to keep in mind is that these numbers m and n have to be experimentally determined. They are not the stoichiometric coefficients in the balanced chemical equation. Okay, so these are found out experimentally. Now, just looking at this expression, we could remove the symbol of proportionality and change that with an equals to sign and a constant k. This constant is called the rate constant for this reaction. So let's just spend a minute and understand what we mean by these numbers m and n. So those are called the order of the reaction. So m is the order with respect to A, n is the order with respect to B, and if you add up m and n, then that is called the overall order of the reaction. So then the question is, okay, you're calling them order, what does that actually mean? So let's take some examples and maybe that becomes more clearer. So if we say that the rate of the reaction is zeroth order with respect to something A, then what we are saying is that the rate is K concentration of A raised to the power 0, because m is 0 in that case, which basically gives you the rate law as rate equals K, because anything raised to the power of 0 is 1. So now what would happen if you change the concentration of A, if you double the concentration of A to 2A? Well, the rate would still be K. So the rate does not change. And that is what zeroth order is saying. It is saying that A actually has no control or no impact, zero control, zero impact over the rate of the reaction. What if m was equal to 1? Then we would get the rate law as rate equals Ka. And now if you change the concentration of A to 2A, what happens? Well, the rate becomes K times twice the concentration of A, which becomes twice Ka. And if this was the first rate, then the second rate, rate 2, is twice of the first rate. Which means that by doubling the concentration of A, you have also doubled the rate of the reaction. And that's what we mean by order. So when the order is 1, whatever you do to the concentration of that substance, so if you triple the concentration of A, then the rate also triples and so on. Now what happens if M was 2? So if the order with respect to A was 2, then your rate law would look something like rate equals K A squared. And now if you change the concentration, if you double the concentration of A, what happens to, so let's call this rate 1. So what happens to the rate of the reaction? Well, the rate would be 2A whole squared. You would get K 4 times concentration of A squared, 4K concentration of A squared. So your rate 2 is actually 4 times rate 1. So for a second order reaction where the value of M is 2, when you double the concentration of the reactant, the rate actually quadruples. Okay, so order is telling you how much impact the change in concentration of that reactant has on the rate of the reaction. Okay, that's all it is saying. So the thing to keep in mind again is that order has to be determined experimentally, it does not come from the balanced chemical equation. So maybe to practice reading orders, let's look at some examples. So in this case, the rate law is given to us. What is the order of the reaction? When they say order of the reaction, they mean overall order. So in this case, there is only one exponent, which is 1. So the order is 1. You're given the rate law. You don't worry about whatever is in the balanced chemical equation. You only look at the rate law and the order is 2. So maybe you pause this video and figure out the orders of these reactions. I will write out the answers. Again, we are only looking at the overall order. Just a reminder, order can be fractional, order can be negative. A question on a test would look something like this. What is the order with respect to each reactant? Well, with respect to bromide ion, the order is 1. With respect to bromate ion, the order is again 1. But with respect to the H plus ion, the order is 2. And the overall order would be 2 plus 1 plus 1, which is 4. So overall order is 4. Having looked at order, let us now look at the rate constant itself. So just to recall, for a given reaction, the rate law is experimentally determined. M and N are orders. The overall order would be M plus N. So what is the rate constant? The rate constant is defined as the rate of the reaction when the molar concentration of each reactant is 1. Okay, so that is the definition of the rate constant. Some characteristics of the rate constant to keep in mind are that it is a measure of the rate of the reaction. If the rate constant is higher, then the rate is also higher. Each reaction has a particular value for the rate constant, and this value is dependent on temperature. So if you change the temperature, then the rate constant also changes. However, the rate constant is not dependent on the concentration of the reactants. The unit of the rate constant depends on the order of the reaction. Now, this thing is important to pay attention to. In order for us to be able to compare the rates of different reactions that have different orders, we keep the rate of the reaction always having the same units. So in general, those units would be moles per liters per second, or you could also write that as a capital M, which is already moles per liter. So you could write molarity per second. In order to keep the units of rate itself same across different types of reactions, we actually have to change the units of the rate constant. So let's figure out what the unit of the rate constant would be for each kind of order. So if the reaction is of the zeroth order, the units for rate are still moles per liter per second. And in order for both sides of the equations to balance, the units for rate constant would also have to be moles per liter per second. Now, what happens when we look at a first order reaction? So, the units for rate, we said we want to keep constant. We don't know the units for K. We are trying to figure that out, but we already know that the unit of concentration is moles per liter. So, then the only units for K that would make this equation true would be per second. So, the units for a rate constant for a first order reaction are per second. Now, what happens when you have a second order reaction? Again, we will keep the units for rate constant, moles per liter per second. We are trying to figure out the units for K. We know that the units for concentration are moles per liter, and we square that. So now we are trying to figure out what's the only thing that works for the units of K. So we are sort of reverse figuring out the units for the rate constant that would make a second order rate law true. In general, you could come up with a formula for figuring out the units of K for any order. Since most chemical reactions are written in terms of concentration, in general, the units of K for a reaction that is nth order would work with this equation. Similarly, if you were talking about a gaseous reaction, instead of concentration, we could be talking about pressures, and in that case, the units of K could be written in terms of atmosphere.